Well, hello. It's good to be back. Now, today I'm going to talk about camera lens design from somewhere in the early 18th century through to just before the Second World War. So, this is a lens. It's a biconvex lens, convex both sides. That is, it's thicker in the middle than it is at the edge. And this is also a lens. This is the Helios 44-2, about which I will be doing a video later. Now the question is, why is this thing here so much bigger than this? What's inside this and why? Now, the first lenses did look like this. They were okay as magnifying glasses or for setting fire to things, but for telescopes and microscopes, they had a lot of what we call aberrations. Now, it's a little unfair on lenses to call these aberrations, for they're all natural properties of spherical lenses. It's just that a perfect spherical lens does not behave perfectly optically. Now, first, let's clarify what we mean by a spherical lens. Here's a sphere. Well, it's a soccer ball, but it's a sphere. Now, let's draw a circle on here, and this part then could then be the surface of a spherical convex lens. That's what it would look like. If you transport yourself to the inside of the sphere, and that sphere would be a concave lens. Now, it just turns out that the simplest way to make a lens with known properties is to make it spherical. And all lenses, up to the beginning of the computer age, have been pretty well spherical, and most still are, though you will find more complex lenses containing molded aspherical elements, that is, non-spherical. Now, the first applications of lenses were for telescopes and microscopes. And this is the design of a simple Galilean telescope, named after, you guessed it, Galileo. And it's an astronomical telescope. The lens at this end is called an objective. It's a convex lens. And the lens at this end is called an eyepiece. And in these early telescopes, this was just a concave lens. Now, it magnified things pretty well, but the images suffered from aberrations, as we mentioned before. They weren't terribly sharp, and there were coloured fringes around the edges. Now, the aberrations, as I said, weren't really faults. As I said before, they're simply features of the way light behaves when it passes through a spherical lens. Now, I'm using a web-based program, an open source program called Ray Optics Simulation, to draw lens diagrams in this video. The link is in the description. I'm going to start by demonstrating spherical aberration. Now, this is the program interface. Here under glass, I can choose either an ideal lens or a spherical lens. I'm going to start with the ideal lens. And we can see it's represented simply as a line with arrows at the ends. The arrows point up and out for convex lenses, so it's like the ends of convex lenses. Traditionally for concave lenses, the arrows would sort of point inwards. You notice it has no thickness. It's an ideal lens. Now from over here, I'm going to select a light beam, and I'll draw it here. This gives us a beam of parallel rays of light, and the program now simulates how those parallel rays of light interact with the ideal lens. Now, this is a convex lens, as I've said, and it focuses light onto a single point, as we would expect. This is the magnifying glass type lens, and it's what we use to focus the sunlight, the sun's rays, onto a piece of paper to set it on fire, or onto our friend's hand when he's not looking, to give him a bit of a burn. Cruel people, aren't we? Now, we know from experience, though, that if we take a magnifying glass and use it to do this, to focus the sun's rays, it comes to a spot, but never to a tiny point. It's a small enough spot, we'll get the paper smoldering, if we're lucky, but you won't get that tiny, tiny point. Now, let's draw a spherical lens, a glass lens in the simulator, like this, and we can see what happens now with a real spherical lens. The rays of light don't focus to a point. They're sort of focused across an area or a distance. So this variation in focus point is called spherical aberration. We can reduce it if we place a stop in front of the lens like this. Then we see that rays of light close to the center of the lens do focus to the point. But the problem with using a stop is that less light gets through. It's called a stop because it's stopping light. Now, all the stop consists of is a disc or a rectangle or a piece of metal or cardboard with a circular hole in it. Now, another problem arises from the fact that white light is actually composed of a range of different colors, varying from red to blue and beyond. Now, in reality, the colors are qualities that only we perceive. The light has different wavelengths that we perceive as different colors. Now, when a ray of light enters a block of glass or a glass lens or water, it's bent like this. The amount of bend depends on the wavelength or color of the light. The bending is called refraction. Blue light is bent more than red light. As a result, white light is split into its constituent colors, and we call this splitting dispersion. The classic example of this is when a glass prism splits light into a rainbow, as in this diagram. Now, the same thing happens when light passes through a lens. We can see that simulated here. Different colors of light focus at slightly different points. We call this chromatic aberration. Modern lenses mostly eliminate chromatic aberration, but you can usually see it on the edges of highlight areas, more on some cheaper lenses than on others. There are other types of aberration apart from these two. Now, these next three are all off-axis aberrations. That is, they occur when the rays of light are coming not straight down the center line of the lens, but from the side. And they are astigmatism, coma, and field curvature. Astigmatism arises when you're off to the side of the lens. You imagine that you're looking at the lens, and instead of looking at it straight on, you're looking at it side on. So it's not as wide as it would be if you're looking at it straight on, but it's still the same height. And what happens then is that rays of light which are in this vertical direction focus onto one point, and rays of light which are like this focus on a different point, two different points. And that's called astigmatism. Now, it's more complicated than that, but that's good enough for beginners like you and me. Now, with coma, you can imagine that if you've got a circle of light, a circle being projected onto the center of the lens, and that'll be a circle. If you then move off to the side, it's not going to be a circle anymore. It's going to be a different shape. You might imagine it's going to be sort of elliptical. Actually, it turns out to be something like a comma shape, or like the shape of a comet. So you've got a sort of a circle, but then you've got a tail coming from it, like a comma or a comet. That's why it's called coma. Again, it's more complicated than that, but that's all I've got for you right now. We could get very, very complicated with this stuff, but it sort of makes my head spin. So I'll save you from that. And the third one of these is field curvature. Now, you start off with a flat object, and the rays of light go from the flat object through the lens and come out the other side, and you get an image which is not flat, it's curved, because you've got a curved lens. Now, this causes an image to be sharp in the middle, but more blurred as we go to the outside. So if you focus on the center of a distant object, the center will be sharp, but it'll be increasingly out of focus as you go to the edges. This was a problem up until the 1890s. It wasn't until then that the problem of field curvature was solved to at least some degree. It's said that if you wanted to photograph a room, it would be best to photograph it from a corner. You stand in one corner and aim your camera towards the other corner, and then you focus on that corner, and then this field curvature would cause the sides of the room, which are closer to you, to be in focus as well. So you could make use of field curvature to get a sharp image if you photographed in that way. Now, as I said, aberration is a complicated subject, and I'm only skimming the surface of it here. Aberrations can be corrected by building the camera lens from a number of lens elements. That's why we get this size of camera lens, because this has got a number of different elements inside it. This one's got six elements, 6 separate pieces of glass. And in a zoom lens that I was looking at just recently, there are 18 elements. That's a lot of complicated pieces of glass. And some of those 18 are actually molded aspherical. So most of them are spherical lenses, but a couple of them are aspherical. So they've been made deliberately non-spherical in order to correct spherical aberration, I believe. Now, as I say, they're molded. So they're not ground, they're molded by casting the hot glass into molds. Now, there are 6 basic possibilities for lens elements that can be used to comprise a camera lens. I'll go through them. Double convex. This basically converges light rays, and it's called a positive lens. Now, the 2 sides don't need to have the same amount of curvature, and it looks pretty much like a simple magnifying glass. Remember that in these diagrams, what we're looking at is what the lens would look like if we sliced it down the middle. The next one is the double concave. This diverges light rays, and it's called a negative lens. Plano-convex. Convex on one side, flat on the other, and this is again converging. Plano-concave. This is concave on one side, flat on the other, and this is diverging. Now we have convexo-concave. It's convex on one side, concave on the other. But the convex curvature is greater than the concave curvature, so this lens ends up being a converging lens or a positive lens. It's also called a meniscus lens, or in this case, a positive meniscus. The concavo-convex lens is also called a meniscus lens. It's very similar to the convexo-concave lens, but in this case, the concave side has greater curvature, and this lens is diverging or negative. Now, each of these elements on their own has the same set of defects or aberrations as we've mentioned before. Correction of chromatic aberration goes back to at least 1730 or 1733. That's well before cameras and photography. And that's when Chester Moore Hall designed what's called an achromatic couplet. That's a pair of lenses made from 2 different glasses, crown glass and flint glass. Now, these two glasses have slightly different, what we call indexes of refraction, so they bend light slightly differently, but they also disperse light differently. And if you work out the right curvatures, you can get one of the lenses to reverse the dispersion that the other one causes. So one of them splits light into its colors and the other one puts them back together again. Well, that's the theory. In practice, it's more difficult than it looks. Chester Moore Hall used it to build the first achromatic telescope. He was a man of independent means, and he didn't care much about commercializing his discovery. Indeed, he tried to keep it a secret, because he designed the two lenses that were the two parts of his achromatic couplet, and he sent the design for one of these lenses to one lens maker and the other one to a different lens maker, so they wouldn't know what he was doing. Unfortunately for Chester Hall, the two lens makers independently reassigned or subcontracted the work to another lens maker, and as it happened, they both subcontracted the work to the same lens maker, George Bass. And George, being a fairly cluey guy, saw the two lenses, worked out that they fitted together, and worked out what they were for. So George dutifully made the lenses, sent them back through the other lens makers to Chester Hall. And then he decided he'd make a few of them for himself and set up, well, he was a lens maker after all, so he started selling these achromatic doublets or couplets himself. Now, George didn't make a lot of money out of that. He wasn't the world's greatest businessman. And Hall didn't patent his design either. So other people started using these lenses independently without restriction, because there was no patent on them. There was no restriction. It was sort of in the public domain, as it were. Now, a bit later on, science or mathematics caught up with practice, and the mathematician Leonard Euler, whatever, I'm going to call him Euler, he wrote a paper explaining how chromatic aberration could be reduced mathematically. This is purely theoretical work, mathematical calculations. He did design a lens which was made up of a glass lens and a lens made from water, if you believe, but he was never able to make them work or to get someone to make them work. Now, John Dulland apparently read Euler's paper and reinvented the achromatic doublet, and he patented his design in 1758. But he didn't enforce his patent. Now, he had also been told of Hall's work by George Bass, so the level of his creative input into the achromatic doublet has been debated. But it does seem he did do a lot of independent research work towards this design. As I say, he didn't enforce his patent. He didn't want to make money out of it. He wasn't that kind of person. But his son Peter, well, he was that kind of person. Peter later patented the design in 1758, and this caused a lot of ill feeling among other lens makers who'd been using that design for some years. And now they found they couldn't because it was patented, and they'd have to get a license from Dulland. They took Dulland to court over this, but the judge upheld the patent, saying that it was the person who exploited the lens or the design for other people to use who was entitled to the patent, not the person who put it in the cupboard and kept it a secret. Dulland was very much a businessman, and the Dulland company, a family company, went on to make a lot of lenses and telescopes and optical instruments. Now, the achromatic couplet corrects only for two colors of light, so it can get red and blue, for instance, to focus in the same plane, and other colors then have to find their own way somewhere in between. So there's still some chromatic aberration left over. Now it is possible to correct for 3 colors, and when you do that, you get a lens called an apochromatic lens. Now the very early history of lenses is somewhat blurred. It's very hard to find out exactly what was going on before somewhere around the mid-1600s or so. The precursor of the camera was the camera obscura. Now this was a system of lenses and a mirror or a prism which projected an image of the outside world downwards onto a table. And you could come into this darkened room with the table in it, and you could look down at the table and marvel at the scene from outside being played out on the table in front of you. Now it used a convex lens initially, and because of field curvature and spherical aberration, the image could be sharp in the middle but got very blurred towards the outside. In 1812, Wollaston found that using a meniscus lens, a positive meniscus lens with a carefully placed stop, the image could be made better. We've seen the meniscus lens before. Looks like this. Now, Wollaston wasn't just a dabbler in optics. He was a very well-known scientist in his time. He started out in medicine, inherited or was given a large amount of cash, and gave up medicine and just amused himself doing science stuff. He did work in electricity, chemistry, medicine, and he developed a secret method for processing platinum ore, which made him very rich. And he kept it a secret pretty much up until his death. So, what was the advantage of the Wollaston Meniscus? Now, this is the problem that the simple double convex lens has: field curvature. In a simulator, we can see how the focus moves away from the image plane as the angle of the light changes. Consequently, the image is reasonably sharp in the center, but really blurred towards the edges. And now, the Wollaston. Initially, it looks terrible. The secret is in the use of a stop. A carefully placed stop in front of the lens makes a dramatic difference. Now, of course, this does result in a loss of light, and the image in the center is not as sharp as for the double convex. But overall, the image is much better. It still suffers from all the other aberrations, however, notably chromatic aberration, but the Wollaston Meniscus was adopted for photography nevertheless. There was nothing better at the time. Now, in 1839, the French lens maker Chevalier improved the Wollaston Meniscus by splitting it from one lens into two and making it an achromatic doublet. The two parts are cemented together, so it's a cemented doublet. This corrected it for chromatic aberration. I have created it here in the simulator, together with the Wollaston. Same outer curvatures, but the inner cemented surface is diverging, so the focal length is increased. The lack of a defined focus point is the same as it was for the simple Wollaston. Now, once again, lens behavior is improved by the use of a stop. Chevalier's lenses were already being used in Daguerre's cameras, and the landscape lens quickly became a standard. But it was very, very slow still. 20-minute exposures, okay for landscapes, but for portraits, not so much. Then, in 1840, an international prize was offered in France for the development of a faster lens. Joseph Petzval, a mathematics professor from what is now Slovakia, took up the challenge and developed the mathematics necessary to calculate the required properties of the lens elements. Now, this required a lot of calculation, and he hired or obtained the use of a number of gunnery soldiers from the Austrian army to do the calculations. Now, you may well ask yourself, what do soldiers know about mathematics? Well, gunnery is a complicated process. A lot of mathematics is involved in making sure that the shell lands where you want it to. So these gunnery soldiers, or cannoneers as they were known, were used to doing mathematical calculations. However, it took a dozen of them 6 months to do the calculations for Petzvald's lens. He then entered the lens in this French competition, but he didn't win because, well, he wasn't French. Now, once he had the design, he engaged Voigtlander to make the lens for him. Voigtlander saw the potential of the lens, and after providing Petzvald with a few samples, he proceeded to make and market the lens for himself. Petzvald had a patent, but only in Austria, and Voigtlander moved his production to Germany to circumvent the patent and produced some 60,000 Petzvald lenses over 20 years, selling them as the Voigtlander Otoscope. It was an immensely successful lens, as it allowed for portraits to be made with exposure times of only a few seconds compared to many minutes. Now, it was very sharp in the center of the image, as well as being fast, but it was increasingly blurred and going towards the edges because of field curvature. Now, this was generally not a problem for portraits, more of a positive feature, in fact. Indeed, modern versions of the Petzvald are made today to take advantage of this. People seeking bokeh are very entranced by the idea, and they buy this expensive version of a very old and imperfect lens so as to have some sort of point of difference with other photographers and videographers. Now, Petzvald also made a landscape lens, but eventually he abandoned optics altogether after losing all his notes and manuscripts in a robbery. He retired to an abandoned monastery in the mountains somewhere and devoted himself to study of acoustics and other branches of science. Now, the next development in lenses related to the symmetrical design. Symmetry is capable of reducing many aberrations. You have two sets of lenses which are pretty much copies of one another, and the aberrations that are introduced by the front set are cancelled out by the second set, provided you've done your calculations. Now let me explain exactly what I mean by symmetry. First, let's go back to 1817, where the mathematician Carl Gauss designed the Gauss telescope objective. Now, this doesn't look, at first sight, a lot different from the typical achromat, but whereas the achromats were generally cemented pairs, Gauss' objective is not. It's two separate lenses with an airspace in between, and it enabled both chromatic and spherical aberration to be corrected. It wasn't terribly successful, it wasn't taken all that much notice of, but around 1888, Alvin Clark took two Gauss objectives and arranged them back to back, as we see here, in the simulator. Now, I've used the actual curvatures from Clark's patent application in the US Patent Office. Clark created this for Bosch and Lomb, I believe. Now, it wasn't the first symmetrical lens, and it wasn't particularly notable either. Now, Dallmayr and Steinhell had independently designed symmetrical lenses way back in 1866. In his patent application, Dallmayr included a very indistinct diagram without measurements, showing two cemented achromats with a stop in between. The lens in the patent was not fully symmetrical, though, as the rear achromat was smaller than the front one. Now, Dallmayr later changed the design to make both the front and the back elements the same diameter, and then the lens was sold as the rapid rectilinear. it had a relatively flat field curvature. It's asserted that the two lenses, the rapid rectilinear and Stanhou's aplanatic, were very similar, and that the two inventors consequently accused one another of copying each other's work. Symmetrical design can inherently correct coma, distortion, astigmatism, and chromatic aberrations. Spherical aberration and field curvature, however, do remain a problem. But major advances were to come. Enter Carl Zeiss. He had set up and run a microscope-making business throughout the mid to late 1800s. Now, he believed, among other things, that lenses should be calculated rather than being developed by trial and error, because although calculation was possible at this time, most lenses were probably made by trial and error. Gifted lens makers got a feel for their art and were able to proceed quite quickly to a suitable solution by trial and error. Now, the problem was that the calculations took so much time. If we remember, Petzval had a dozen human calculators working for 6 months to calculate his lens, and it still had shortcomings at the end. In the second half of the 1800s, Zeiss began a collaboration with the physicist Ernst Abbe and the glassmaker Otto Schott, and things changed greatly. Schott developed new glasses with greater ranges of refractive index and dispersion. This allowed greater scope to correct aberrations. And Abbe provided the mathematical methods to take advantage. Zeiss was the driving force, though. After his death in 1888, Abbe, an astute businessman, continued his work, setting the business up as a foundation. At this time also, the Zeiss company started making photographic lenses. Heretofore, they'd only made microscopes. This was the influence of Abbe. Well, the next landmark, then, was the creation of the Zeiss planar lens. This was designed by Paul Rudolph in 1896, working, of course, for Zeiss. It's based on the double Gauss, but the inner meniscus elements have been thickened up and made as achromatic doublets, as you can see here. I've created it in the simulator using the measurements in Rudolph's patent application. Now, Rudolph does not specify lens diameters, so I've had to estimate them from the diagram in the patent. The similarity to the double Gauss is obvious. The inner biconcave elements were of flint glass, and the others were of crown. Both glasses were of nearly the same refractive index, but different dispersions. Now, crown and flint glasses can be of quite different refractive indices, but using different varieties of these glasses, you can get both of them to have approximately the same refractive index, but different dispersions. And this is what Rudolph has specified in his patent. Now, according to his patent application, the lens is not only spherically and chromatically corrected, but also anastigmatically flattened, indicating that the field curvature was minimized. This relatively flat field curvature gave rise to the name planar, which means flat. Now, this was an immensely successful lens design, and you can still see the planar name on Zeiss lenses today. Modern planar lenses are very different from the lenses that existed in the time of Rudolph, because we have a much better range of glass types, and of course we have computers to do the calculations. Now, there were many other lens designs appearing all the time. For instance, the Zeiss Anastigmat of 1890 and Rudolph's Tessar, the name of which, once again, is still in use today, although the modern lenses bear only a superficial resemblance to the original Tessar. The Tessar is used in phone lenses, the lenses for phone cameras, and these lenses are extremely aspherical. They're very, very strange-looking lenses indeed. Well, I'm going to ignore all of these other lenses, I'm afraid, and I'm going to jump forward to one of the major improvements or derivatives of the planar, and this was the Zeiss Biotar. Dr. Willy Merte worked at Zeiss for many years in the early 20th century, and in 1927 he patented the famous Biotar. His description in the patent application is headed objective, corrected spherically, chromatically, astigmatically, and for coma. It's similar to the planar, but the last element has been changed into a biconvex element, and he worked the calculations for corrections for the lens as a complete system, rather than element by element. It was originally released as a 50mm f1.4 for cinema. Later, in about 1936-37, it was an option for the Kina Exacta, the first modern single-lens reflex photography camera. And for this, it was released as a 58mm f2. Now, it's believed that it had to be 58mm because the mirror box in the camera placed the 50mm too far forward to focus, so it had to have a longer focus at the back. However, having said that, if we look at the brochure for the Kina Exacta, we can see a choice of lenses, including the Zeiss Tessar 50mm and other 50mm lenses, so that doesn't quite add up. Now, that takes us anyway to the Second World War. After that, computers were used in lens design. It was a whole different ballgame. Lenses could be developed in weeks rather than months. Petzval, as I've said, needed a dozen human computers for 6 months to calculate his portrait lens. The calculations for the Biotar, it is said, required 480 steps and 3,200 pages, with 2 human computers working for 3 years to complete them. Now, using computers condensed the time into hours, and the discovery of new glasses incorporating rare earths enabled easier and more accurate correction of aberrations. So this is a logical place to stop. There is one post-war development that I will cover, however. This is the Helios 44M 58mm f2. Sound familiar? Well, it should do. This lens is a copy of the legendary Zeiss Biotar 58mm f2, and today it can be picked up for less than $100. After the war, Germany was divided up into 4 zones controlled by the US, the UK, France, and the Soviet Union, otherwise known as Russia. Though the Soviet Union isn't the same as Russia. The Soviet Union was a union of states, pretty much like the United States of America, and it consisted of a number of countries, of which Russia was probably the biggest. Now, the part of Germany that the Soviets got had the Zeiss Jena factory in it, and they acquired all the technology, all the what was left of the factory, and the personnel. Now, they couldn't, however, continue with the production of the Biotar because they didn't have access to the glasses used by Zeiss, and they had to recalculate the lens for glasses available to the Soviet Union. Now, once they'd done that, they manufactured the lens under the name of Helios. Same lens, different glasses, and the structure of the lens looks pretty much exactly the same as the Biotar. Now, it was this lens, this particular one, that inspired me to make this video. The Helios has gained cult status today among photographers and videographers, though in its day it was despised as cheap with questionable quality control. In fact, my first 35mm camera was a Soviet Zenit E with the Helios 58mm f2 lens. It was the cheapest camera on the market at the time, or at least the cheapest 35mm interchangeable lens camera. Today, the Helios owes its popularity to its imperfections. Photographers and videographers have become jaded with the perfection and sharpness of modern lenses and are looking for a point of difference. They're looking for a lens with character, something with a unique set of imperfections. In particular, the Helios has what's known as a swirly bokeh, at least under certain circumstances. And that's caused by uncorrected astigmatism. Now, many people find this attractive. Personally, I find it rather busy and unattractive, but it's a matter of taste. Now, the Biotar actually had the same fault. People would buy the Biotar for the same reason, except that the Biotar is much, much harder to find, and when you do find it, it's much more expensive. You see, the Russians, once they perfected the Helios, they made millions of them. It was probably the most mass-produced lens for an interchangeable lens camera ever. Now, I will review the Helios in a future video. In the meantime, get out there and make art. Don't forget to like and subscribe, and I'll see you in the next video.